UKMARSBOT. I'll skip the customary introduction about the robot itself. You've probably all seen enough details of it now. And some time ago, I perhaps rashly promised that I would show it running in a maze to prove that it can be done, that it wasn't all a terrible misadventure. So what I want to do tonight, though, because this is all horribly misleading, is to just have a look at some of the software needs that get you there, because everything's been posted up on GitHub for people to look at, download, use, and apply to their own robot or to similar robots. And none of this all happens in isolation. My particular MarsBot is called Dorothy. And tonight I want to really just have a look at some of the things that you need to think about in the software when you're trying to write a maze solver. I'm going to have a look at managing the complexity of it, because it may seem straightforward in ways, and then you very quickly go down a rabbit hole of unpleasantness as you try and work out how to do all these things. We'll have a brief look at how you can make the code that I have provided work. We'll have a look at some of the issues around managing the various tasks and the sensors. The encoders present their own particular challenges, especially on this robot. We'll have a look at how you manage movement and control it. We'll have a look at how it all goes together. There's a little bit about atomic access, which I won't explain now, just to keep you wondering as we go through. And then I will actually show it running. So the thing about Micromouse software, like a lot of robot software, is that there's an awful lot to do. Perhaps more than you may have given credit to. You may have looked at the problem, you may have already have written a complete Micromouse, you may have written several sets of robot software. And I think if you have, you will certainly agree that there's quite a lot of things to worry about. I sat down for 2 or 3 minutes and came up with this list. This is specific to the Micromouse problem, but many of those issues exist for any small robot. It could be sumo, it could be wall following, it could be a combat robot, it could even be one that's radio controlled. All of these things need to be thought about, and I'm sure if you've bothered to read through the list that's on the screen, you will have thought, oh no, he's left out this and he's left out that, or whatever. There's a lot to do. It's a complicated system, and it's full of all sorts of different components, and they all link together in appalling ways. So it's pretty clear that if you want to write a maze solver, you've got to be able to plan routes and search the maze, and you may have some need to talk to the user or log information or look at the battery voltage. And the way all these things link together is terrible. If you're not careful, you can find yourself writing them piecemeal and then trying to link them up in code that ends up looking uncomfortably like this. But if you give it a little bit of thought, you can start to group some of these things together. And when you do that, some things become apparent. So in green, you'll see all of these things are to do with the processor and with the board itself. And in orange, you have objects or entities or whatever you want to call them, which make use of those. So the encoders are going to be using the timer and the GPIO, perhaps, to get information out of them. And the motor might use a PWM unit and so on. And those objects are all going to get used by the robot itself. So a maze solver will need to be doing some planning. A line follower will need to be doing some planning, but they may or may not be the same kind of planning. They have different kinds of sensors, but in the end, they still have to talk to the same analog to digital converter and so on. So if you take these things and try and unscramble them and put them into some kind of order, you might end up with a model that looks a bit more like that. And at the bottom, you've got all of the stuff related to the processor itself and the actual robot hardware. And then in the middle, you have the objects which would use that hardware and provide information and services to the objects above them. Everything below the word robot is just that. It's the robot. So it could be a maze solver, a sumo robot. It could be a firefighting robot. It could be almost anything. But it'll make use of those parts underneath. UKMARSBOT is intended to be driven with an Arduino Nano. Now, we chose that partly because it was possible to plug other processors in. And indeed, people have plugged all sorts of processors in and they work just fine. But of course, the Nano has a particular way of implementing timers and I2C and SPI and all that, which may not be true for another processor. So somewhere down there, at some point, there will be some need for hardware abstraction. My code doesn't look disorganized, I have to be honest. It's getting there, but it doesn't look like it yet. And if there are people who want to take the whole challenge up and want to use other processors with more memory or different peripherals or whatever, then I would appreciate some help on that hardware abstraction side of things, where we can start to make it a lot more versatile than it is now. So as I said, all the code is up on GitHub. You can download it. It's based on the Arduino framework because that's perhaps the most widely available and understood framework there is for microcontrollers. It's only intended to work with the Nano, so if you want to try and use it, even with the Nano Extra, you might find that some of the hardware is different. I think the Nano Extra is mostly the same, but it doesn't have EEPROM, for example, so you can't save settings. However, it's a moderately complicated program, and there are quite a few files, and that, if you're not used to that kind of development or that kind of program structure, it may upset you briefly. It's been built on and works with in 3 environments at the moment: the Arduino IDE itself, Platform IO, and Eclipse using the Sloeber plugin or distribution. If you're using the Arduino IDE, you have 1 or 2 small problems to deal with. It's quite old now. Even the Arduino people are looking forward to something else. Mostly, Arduino users are used to simply opening up a file with everything in it and working from that. And whilst you can open the Mazerunner.ino file in the Arduino environment and everything will build and program and run perfectly well, you might be surprised to find a dozen other files opening at the same time and cluttering up the screen and leaving you with no obvious easy way to find your way around. Sorry, but things have to move on. There's a note here about the bootloader. I don't think you have to worry about it for the Arduino IDE, but in other places you should be aware that cheap clone Nanos use an old version of the bootloader, and sometimes that has to be specified. The newer Nanos use a faster bootloader. So it's just a memoir, an aid memoir to me, really, just to point that out. I've developed everything using Visual Studio Code and Platform IO. And the repository up on GitHub is exactly that. It's a Platform IO project, which can be opened directly in Visual Studio Code. And away you go. And I've just reminded myself that I didn't put in the YouTube link. But I will do that later. There is a YouTube video. It's on the UKMARS channel. And you can follow the instructions and download and install Visual Studio Code and Platform IO. Once more, as I seem to every time, I recommend it. You can use it for building for any number of different targets and frameworks, RTOS, Arduino, all kinds of things. It's much, much better. And it's not just about embedded stuff either. You can use it for desktop development, Python development, all sorts of stuff. For the more intrepid among you, like Rob, you can use Eclipse and Sloeber. And I was going to ask Rob to do this, but I did my timings earlier, and I want to kind of dash through things a bit, so sorry, Rob. But Rob sent me these instructions. It's quite easy. I've used it myself. Eclipse, I don't know if you've used it, but Eclipse is very comprehensive. It's quite what's the word I'm looking for? It's a well-established big build IDE, and it will do all sorts of stuff. And Rob has graciously added the Sloeber configuration details to the project, so you can just load it up and go. What's that? Right, so the code itself. Now, bear in mind that this is a work in progress, right? Only yesterday did it finally get to the stage of demonstration that you'll see later, and there's plenty more to do yet, notably in terms of tidying up. But the functionality is pretty much all there. We can do all the sensing. I can do the steering and drive the motors. I can read the encoders reliably. There is a user interface. If you want to put a Bluetooth module on it, you can do that, and you can interact with the thing directly and adjust the settings, give it commands, log data straight out. All of the motion profiling is now configured and working, and you can load and save the various settings. So you can adjust, like, maybe the steering constant or the controller constants, and you can adjust those on the fly over Bluetooth and then save them off to EEPROM and sort them out later. One of the great things that I've tried to make sure of is that everything is in real units. So the motor drive is not in PWM numbers, it's in volts, right? The distances are in millimeters, angles are in degrees. I stopped short of using radians, but they're in units that you should be able to understand. So you don't have to worry about how many clicks per degree of turn it takes or anything like that. You just tell it you want to turn 90 degrees and you'll get 90 degrees. Almost certainly. I should put this is a fair place to point out, by the way, that the encoders are fairly low resolution, and the actual resolution is only about half a degree, which doesn't sound like much, but it turns out that over the course of a dozen turns, that can add up, right, if you're not careful. So the linear resolution's about, I think, about 0.4 millimeters. So it's pretty coarse stuff in many ways. So although the robot itself appears fairly straightforward and simple, I mean, there's not a lot on it. If you look at it, there's a few sensors, all of the hard work's done in the processor board, right? And you don't even have to do that. It's quite typical of a lot of mobile robots. It's certainly fairly typical of a lot of Micromouse robots and line followers and so forth. And the idea of the project was that if you get to drive this, you have transferable skills, right? If you can learn how to work this robot, you can learn how to work almost any small-wheeled mobile robot. It's a good basis. But there are nonetheless several components that have to be managed. And there are lots of tasks that have to be looked after. And these have to be done in a timely fashion. You can't just go off reading stuff when you feel like it and hope to get something sensible out of it. You wouldn't be driving down the motorway reading a book and thinking, I better just check that I'm still in lane, right? You have to pay attention to stuff, and you have to do stuff in the right order at the right time. And because this is not the world's most powerful processor, you have to be fairly efficient about it too. So if you've done any Arduino work, you're familiar with the idea that all of the code sits in the main loop, right? Typically, people do a bunch of hardware setup in setup, they go off the loop, and then they just sit there and everything happens in the foreground. And a typical Arduino application is really remarkably simplistic. But as soon as you get beyond something more complicated than measuring the temperature in your room or controlling a sous vide cooker or something like that, you start to realize that actually it all gets quite tricky, because the order in which events happen is important. The time that they take, if tasks have different priorities. So, for example, the encoders, you can't miss an encoder. You can't just go and have a look and see what the encoders are doing. Something has to keep track of that properly, right? And things happen at different, Can somebody wave if they can still hear me? Okay. My laptop has lost its network connection.
I can still hear you.
Okay. So codes must keep changing task. Your main user code will have to keep changing task all the time to keep up with stuff, which is an absolute nightmare. Derek, we'll need your recording. My laptop's died. So one way to try and make sure that this happens is to divide your task up. And typically that is done by having some kind of regular interrupt. I call it the Systick interrupt because that's what it's called in the STM32 processor stuff. And on UKMARSBOT, we've got an interrupt happening. One of the timers fires off every 2 milliseconds. So 500 times a second, the main code is interrupted, and we often do routine tasks. And I won't insult you by describing what interrupts are about, except to remind you that the context is saved, right? So you don't even notice that anything's happened. So what happens in this Systick interrupt? Well, there are 3 or 4 main tasks. One of them is to read the encoder information. This doesn't mean checking the pulses. This means checking how many pulses have occurred since the last Systick interrupt. So that's a measure of how far we have gone and how much the robot has turned. Then we need to read the sensors. So the ADC has to be polled. I read all 8 channels, and I read them twice, once with the emitters off and once with the emitters on. So that's 16 reads, and they can take 30 microseconds. Even when you've turned the ADC up as fast as it can reasonably go without losing information on the Mega 328, it takes about 30 microseconds per conversion. So that's 480 microseconds gone right down the tubes trying to work out what the ADC is doing. That's not good. And then when you've got all of that information, you've got to run the controllers and update the profilers and sort out if there's any serial characters or any of those things. So there's quite a lot going on, and it uses up a fairly large chunk of that 2 milliseconds. More, in fact, than you really want. You don't want to be using up 50% of your processor power just doing this kind of thing. The obvious way to attack this is to have a look at the ADC. And it turns out that, like many processors, the ATmega 328 can generate an interrupt when a conversion is complete. So at the end of Systick, you can fire off an ADC conversion, and there will be another interrupt when it's finished. Collect up the result, start another conversion, return from the interrupt. And what happens then is that at the end of Systick, you get this sequence of very brief interrupts. They're only a few microseconds each, whilst where the details are read, and you get an awful lot more time left for your main foreground tasks. A disadvantage, of course, is that all of your ADC readings are now 1 cycle late, right? And in control terms, that might upset you, but it doesn't make much difference. This is not the world's most high-performing robot, right? It's plenty adequate to be 2 milliseconds out of date. Bear in mind, though, that if you're going 1 meter per second, no, I can't work it out in my head. You've traveled some significant distance anyway, 2 milliseconds, whatever it is, I don't know, a few millimeters. A special case, though, is the wheel encoder interrupts. These have their own interrupt service routine because they can happen pretty frequently. The ISR in the code only takes about 3 or 4 microseconds, but be aware that if you've got high-resolution encoders and you're running hell for leather down the straights, you might get about 30,000 interrupts per second. So you don't want to be wasting time in there. A significant amount of time can be used up if you're not careful. But most importantly, you just cannot miss one, right? So these are on a high priority interrupt. You cannot afford to miss an encoder pulse. I forgot to re-enable interrupts for quite some time when developing this and was driving myself nuts trying to work out why I couldn't drive in a straight line, and it was just because I was missing encoder pulses. I just overlooked it. Stupid, but there you go. So motion. To make the robot move, we use what you might call a V-omega model. You have forward motion, you have rotary motion. These are completely independent and can be combined into any possible motion that the robot can make. Clearly, if you're moving forward at constant speed and you then apply a constant rotation at the same time, your robot will move around in a circle. If you apply a constant rotation, but you're not moving forward, it will spin. It sounds straightforward when you describe it like that. It's slightly tricky to put together, but it's a very common way of controlling a wheeled mobile robot. And it allows for some quite nice, easy modeling and some quite nice, easy processing. It certainly allows for quite convenient control. If you've built robots before and you've done so by trying to control the individual wheel speeds, you're asking for trouble, I'm sorry. It's just not easy to write the code which says this wheel must be going this fast, this wheel must be going that fast, how fast must they be going to perform this maneuver or whatever. So this is the kind of information that you get out of it. You can see the orange with grey overlay is forward motion, and the blue with a yellow overlay is rotary motion. The grey and the yellow are the information coming back from the encoders, and the orange and the blue, which you can't see very well, are what is commanded. The reason why the encoder information is very spiky is just because the resolution of the encoders isn't very great, and 1 or 2 counts makes quite a difference. So you can be late for a count, miss a count, catch it up next time, and that shows up as noise in the output. But I think you can see that overall it gets the job done and goes where it has to go. This trace represents the robot sprinting forwards, slowing down to 300 millimeters per second. At that point, it starts to turn. It's a coincidence that the angular velocity is 300 millimeters per second. Once it's done enough of that, it decelerates the rotational component and then sets off again forwards in a straight line, but now at a reduced speed of about 125 millimeters per second before braking nicely to a halt. This motion would look like a sprint forwards in a straight line, a smooth integrated left-hand 90-degree turn, and then a slower exit, possibly over the same distance. I can't work it out in my head. Slower speed, longer time. So you can make any motion that the robot needs to make. And this is true also for the line followers, by the way. It's exactly how the line follower works. Profiles like this need to have 4 pieces of information: distance, speed, max speed, end speed, and acceleration. You could set a default acceleration throughout, but that turns out not to be a very flexible solution. And in the code, you simply say, start a forward movement, 180 millimeters, maximum speed, 500 millimeters per second, finish at 300 millimeters per second, and use 3000 millimeters per second acceleration. Honestly, I couldn't think of how to make it any simpler. Once started, the Systick timer looks after this, and when it's finished, a flag is set, and you can query that with a simple function call. And if you wanted to do a turn, it would just be rotation.start and rotation.isFinished. Just those commands are sufficient for nearly all of the movement that you need. Now, the profilers are generating speeds. They don't care where you are particularly, although they do keep track of how far you've moved and what the angle is, but a profile is simply a set of speeds at any given time, that graph that you saw. The controllers, however, are not velocity controllers. The controllers are position controllers. So on each tick, the control software notes the speed, uses that to work out where the robot should be now, either in angular or distance terms, or both actually, one after the other. The encoder information is used to find out where the robot actually is, and then the controllers do their best to try and make that error zero. And it turns out that position controllers are much easier to reach, at least I think so, than velocity controllers. And they're not a full PID controller, they're just PD controllers. All this goes together with one of these diagrams that you will have seen if you've been unfortunate enough to look in robot books. But it just tells you how the bits and pieces go together. I won't dwell on it too much. Suffice it to say that if you follow the forward path, we take the difference between where you should be and where you are, feed the answer through a PD controller, and the output we get is in volts, right? And it's important that it's in volts, not in PWM counts. Another day I'll explain why, but for now it's just in volts. And if you follow the path, you'll see that that voltage is applied equally to the left motor and the right motor. And if they're the same, and if the motors are the same, the robot will go forwards and the encoder counts will change. And if you follow through the encoders, you'll see that the left encoder plus the right encoder give you the current position. I can see you all scanning the screen, so I'll wait until you stop trying to follow it through. Rotation, same kind of deal, except that we use the difference. And I have used the convention that if the robot is turning left, that is anti-clockwise, that's a positive value, and if it's turning right, that's a negative value. There are two reasons for that. One is that's how maths works. And the other is if you draw a graph like the one that I showed you earlier and you imagine yourself sitting on the x-axis and walking along it, left is on your left and right is on your right. Think about it. It's just kind of easier. Well, it's easier in my head anyway. And finally, the atomic access teaser. The ATmega328 is an 8-bit processor. It's a pretty lowly device in many ways. And the most important things to note are, if you know all this, just, twiddle your thumbs for a moment. Integers need 16 bits, 2 bytes of storage. Floating point numbers need 4 bytes of storage. And we have interrupts going on at anything up to 30,000 times a second. Your code could be trying to read the position, which is stored as a float, get halfway through reading that float, read the first 2 bytes, and then an interrupt happens, all the calculations are done again, and the position isn't what it was when you read the first half, and what you get back is garbage. So you will see, if you look at the code, scattered all over it, these unpleasant atomic block structures, and they are there. They're built in, provided by the compiler tools. They turn off the interrupts so that your access is not interrupted at any time. And then you do what you need to do, which is usually to make a local copy of the variable that you can rely upon. And then the atomic restore state puts the interrupt enable flag back where it found it. It's not safe, if you've done this before, it is not safe to turn off interrupts and then turn them back on, because they may not have been on in the first place. You need to save the state of the flag and restore it. Otherwise, you may be enabling interrupts inadvertently where you shouldn't. So that, fairly lickety-split, is it for that part. And if you'll bear with me a moment, I will stop sharing.